Okay. Okay, so maybe gotta be looking at that. If it slips or something, you gotta let me know. Okay. So we're recording manually because the laptop won't. There's probably people at home freaking out. They're like, "What's it's not going live? Go into the stream." So I'll post this. Although it seems to be like if the video gets too long, if it gets over like 4 gigabytes, it seems to have issues. Okay, so PCBs all look good. The last couple people who have their PCBs, I think I've checked off everybody's schematic and PCB. It's just some last little polishing things. Anybody, again, any of you can revise your board. If you were a little rushed and you want to submit one for tonight, I probably won't send them off to the PCB fab until like tomorrow night. So, so if you want to work on it on Saturday during the day, it'll probably be fine too if you submit it. Just email it to me directly if that's the case. But the plan is probably, as the boards come in, I'll probably give them to people and people can have an opportunity to start assembling them if they want. But we'll do a formal lab after Thanksgiving where we actually do the assembly and test, and we'll go over some formal processes related to that, because sometimes it's useful to not, especially if you're assembling it by hand and not with a stencil, it can be useful to do it part by part. So we'll talk about some of that and how we can do it step by step, and I'll probably post some videos on techniques to do it. I've also just gotten talks with a Makerspace, so they have a laser. It's probably not going to work for this quarter, but for most of you for your senior projects, we're trying to set up like a soldering and PCB certification for the Makerspace. So they have a laser cutter, so if we can get that going, cutting stencils with a laser cutter, that's much better than we have a blade stencil cutter in the 340 lab, but students kind of like abused it a little bit and like broke it, and so we could never keep it up. We can never keep it functioning, so we kind of abandoned it and just said just pay $7 because it's the only way. It also takes about it takes about half a day to cut your stencil out. So like one student with a big senior project board would like hog the thing for a whole day if they, anyway. So, but yeah, so it's pretty cheap to buy them. And hopefully we get the Makerspace able to do the laser cutting of them. That would be really great if we could get that going. But that is on the way, so that'll be the plan for that lab. We also are going to do a little mini lab on converters. The problem with DC to DC switching converters is they don't breadboard well. Modern switching converters are high speed. They don't like the big loops that we have when you do a breadboard. So we've done it in the past, and there's like huge amounts of noise on the circuit that students make. But I wanted to talk a little bit about that. So the homework that is due Wednesday, you say it's due Monday, and that was the case, and then Britney Spears is free, so everybody's going to be playing Toxic on repeat this weekend. Nobody's going to get any work done, because people aren't as excited about Britney being free as me. I was like...
Wait, she's actually free?
I was like apathetic, and then I watched a documentary, and I was like, "This is my Vietnam, okay?" So it's Wednesday, so we'll get a chance to. I'll answer your questions about it on Monday. But there was so the basic idea as you watch the videos, if you haven't already, on the switching regulators is one. There's the linear. Sorry. So, linear regulators. Linear regulators are very common in engineering. They're basically, they're grounded, you have V in, and V in always has to be greater than V out, and then you have V out. And basically all they are is, so internally, these basically take the output voltage that's being produced with a capacitor to smooth it out, and they basically just compare the output voltage. So normally what they do is they take the output, sometimes it's internal, sometimes it's external. That's way too small for anybody to see. But they basically take the output voltage and they compare it with a voltage reference that's internal. And that voltage reference that's internal is basically generated the way we did in that lab where we had the Zener diode. It's a little more precise than what we did with the Zener diode. It's a special way of amplifying a Zener diode, but internally it produces a reference voltage. It compares the output voltage to that reference voltage, and if the output voltage is lower than that reference voltage, it turns on a MOSFET. And that's pretty much it. I mean, this is basically it. It allows current to flow from the input to the output when the output voltage is lower than the desired output voltage. And a lot of these linear regulators have this resistor divider external. So internally it generates like a 1.1 volt reference voltage, and the linear regulator says, hey, take your output, whatever you want it to be, and use the appropriate voltage divider to give me a signal, and I'll let current flow from the input to the output until we reach 1.1 volts on that pin, or whatever the reference voltage is on that pin. So linear regulators are, and ultimately you'll see what happens is similar to what happened in the lab, which is when this voltage gets close, you're sort of rapidly turning this transistor on and off. It's kind of always sort of in this kind of middle of the road state. So linear regulators are great for getting a nice clean voltage signal. And people use them for that. The downside with linear regulators is they burn off energy across this transistor. So the current in equals the current out in a linear regulator. All they do is drop the voltage down. So it's inefficient if there's a big voltage change. If you have an input that's 12 volts and output that's 3 volts, you're going to be burning 75% of your power just dropping that voltage across the transistor. And so we've had, I think I talked about it in the videos, but we've had senior projects where students have a high power application, they try to use a linear regulator, and they smoke the regulator first thing when they run it because they were dissipating so much power. So switching regulators don't do that. They're more efficient. There's a question?
I was just going to say, I hope I'm not the only one here, but did you use a different marker?
Yeah, sorry,
really
yeah.
Hard to see.
Yeah, I was writing tiny with a yellow with an orange marker. So just let me redo the linear regulator so people don't. So linear regulator, basically, it's just this internally. It's a comparator. So they generate an internal reference. I'm going to show the internal reference with a divider, but that's not actually what happens. And then there's almost always a capacitor at the output and input. And then there's so either what they do is they take the output voltage and they automatically run it through an internal divider and do the comparison, or they normally what they'll do is this will be an external pin. So the idea is externally you pick the collection of resistors and feed that back. And all it's doing is just if this voltage is lower than this internal reference, it lets current flow from the input to the output. So this is almost exactly functionally what you had in your project for where we got the constant voltage at 4.2, which is basically just as soon as the voltage got over 4.2, we turned off the current flow. That was just a longer pathway that did this exact thing, basically. It's just using a comparator to turn on or off the flow of current. We're just doing it directly with a MOSFET in the case of a linear regulator. One thing you'll find is with almost all of our power conversion topologies, and we don't have time in class things to go over all of them, but in the videos you see they all use MOSFETs. Why do we use MOSFETs instead of, why do we not use BJTs when we get to this stuff? Pretty much everything in this class we'll use MOSFETs for, yeah.
I mean, aren't MOSFETs just like generally pretty efficient and small?
Yeah,
BJTs are obviously small, but like
right.
MOSFETs can be like really small.
Yeah, MOSFETs can be small, and the size of a thing is normally related to how much heat it has to dissipate.
Yeah, and how cheap it is.
And how cheap it is, right? So a MOSFET is a super efficient on-off switch. A BJT is great for if you're trying to make a current, amplify a current. So if you're trying to have an input signal that actually controls the flow of current, it's difficult to do with a MOSFET. It's voltage controlled, and without some kind of feedback, it's a very fine sort of threshold where this thing is in its linear region. So you normally MOSFETs are super efficient on-off switches. And super efficient, once you get to power conversion, all you care about is things being super efficient. And so one of the common themes you'll see throughout this rest of the class, basically, which is these conversion techniques, is we do whatever it takes to efficiently convert power using on-off switches. And quite often that means you have to produce a ugly changing voltage or current and then clean it up later. And that's what you see with both the buck regulators and the boost regulators in the video series. The idea there is you temporarily store energy in an inductor and then you put it somewhere else. You temporarily store energy in an inductor with a circuit in one configuration. Then you change the configuration of the circuit using MOSFETs as switches. And then in the new configuration of the circuit, the energy that was stored in the inductor gets transferred to the output. Or sometimes to another, the different topologies. Some of them are kind of fancy and they sort of hand energy off from one thing to another. But the ultimate challenge we face with DC to DC converters is we have a DC signal, but things like inductors and capacitors are not useful for moving energy in the DC case. Because, in the case of an inductor, the way you accumulate and discharge energy is by having a change in current. As you increase the current through the inductor, the stored energy increases. As you decrease the current through an inductor, the stored energy decreases. So we almost always have to, big picture, we almost always have to, in one way or another, induce a change of current. And that doesn't produce something that looks very DC. So we got to smooth it out later with inductors and capacitors and filters that clean everything up. So that's, as you're looking through the videos, this is the sort of the basic idea. In AC is wonderful because it's easy to transform. All you have to do to transform AC is have 2 coils of wire. But there's downsides to AC. Mostly you can't power digital circuits with AC power because fundamentally they're all diodes. You can only apply a voltage in one direction, right? Or everything breaks. Okay. So the linear regulator is super important, but inefficient. Although if your voltages are close, linear regulators can be pretty efficient. One common thing is lithium, including the batteries you're charging, has a potential energy of 4.2 electron volts, or 4.5 electron volts, but basically it's 4.2 that you get out of it. And 3.3 volts is a very popular voltage for digital electronics. So the 3.3 volt circuits are a very common style of CMOS logic is 3.3 volt logic. 5 volt logic is also very popular. You've probably seen that when you take digital circuits. And then after that, 1.8 volt logic is pretty popular nowadays. And increasingly, 1.2 and 0.9 volt logic is popular. So, people like to power transistors with lower and lower voltages. Why?
Efficiency.
Yeah, efficiency. Because you need to charge. Digital logic is all about charging and discharging capacitors. If you only have to charge the capacitor up to 1.8 volts instead of 5 volts, it's a lot less energy. It also happens a lot faster. If you're trying to, the time it takes to charge a capacitor up to 1.8 volts is a lot lower than the time it takes to charge up to 5.
You also get to use a smaller capacitor to save money.
You also get to use, that's right.
Yeah.
Well, smaller transistor, right?
Yeah.
The downside is as we go to lower voltage threshold digital logic, the challenge is you start to get a lot more leaking. So 0.9 volt logic, when you're 0 or 0.9 volts, you're not ever fully on or fully off. So they have to do extra stuff to sort of mitigate that because you don't want leaking in digital circuits because then you have constant power loss and that starts to add up. So that's all stuff that's beyond this class. But the basic idea of why we switch voltage, why we need it to be DC, that's important for knowing why we care about DC to DC converters. Almost every piece of electronics you buy nowadays will have a DC to DC converter in it. The cheaper stuff is going to be linear regulators because these cost pennies. The more expensive stuff is the switching, the buck and boost converter, buck boost, choke, which are all ones we talk about in the videos. And the reason they're expensive is mostly because they need to have an inductor. And there's no way to get an inductor that stores a reasonable amount of energy without literally coiling copper around an iron core. And fundamentally, Copper, there's a limit to how cheap it, silicon it's on the beaches, everywhere you go, it's on the beaches, right? There's lots of it, it's cheap. Things like copper, things like iron that is designed for magnetic permeability or permittivity, that's much more expensive. So there's a fundamental limit to how cheap you can make that, I should say. So as silicon devices have gotten cheaper, we've hit more and more that fundamental limit of the inductor. And if you ever look at like old audio equipment used to weigh like 100 pounds. You have like one amplifier that's 100 pounds. And if you open it up, that 100 pounds was one inductor, right? It's like one giant inductor that was like 5 pounds of copper and 10 pounds of iron. And that was normally because that was how you get a nice clean, that's how you get nice clean on, that's how you filter out undesired signals and frequencies. And we can't do that. So the switching regulators we deal with, they've gone faster and faster. If you only want to store a little bit of energy in an inductor, you better move it quickly. You better store a little bit and then move it, because ultimately your power output is going to have to, however much energy you can store in that inductor, that's going to have to be scaled to deal with the power at your output of your switching converter. Boy, this laptop still hasn't started up. What on earth? I'm getting worried now. This thing's bricked. Every time it does this, I worry about it. Okay, so, power amplifiers. We also talk about power amplifiers. This is increasingly, we had a big debate within the program about should we even include power amplifiers in this class. But we decided, if you all become engineers, you probably will never design a class A or B or AB or C amplifier. You'll probably work with class D amplifiers, because the difference is class D amplifiers use only MOSFETs. Class A, B, and C, they all use BJTs. And so, well, class C sometimes doesn't use BJT, but all of those amplifier types are they're naturally inefficient because they don't use MOSFETs. Class D, theoretically, class D could be, infinitely efficient. It could be 100% efficient, technically, in some universe. Whereas class A, B, and C never could. So, but MOSFETs have gotten better, controllers have gotten better to the point where now the full range of audio is pretty easy to produce with a class D amplifier. And the challenge you'll see in the homework and in the assignment is, like with any other time where you're trying to just use MOSFETs, you have to chop up a signal to produce an analog signal. You have to use MOSFETs. You have to have a carrier frequency that chops up a signal. You have to get that carrier frequency filtered out. And so normally that means if you want to use passive filters, which you have to use for power amplifiers, your carrier frequency has to be orders of magnitude, or at least an order of magnitude higher than the magnitude of the signals you care about. So for audio, thankfully we can't hear super high frequency audio, right? The limit of our ears, your ears can probably hear maybe 18 kilohertz. My ears can hear maybe 15 kilohertz just because I'm old. And that happens. I don't know why. I also, every time I go hunting, I forget to bring earplugs. That's really not good. I know it's always like, I went hunting with this guy and he had this rifle that was like, it was like some insane, it was like some like Weatherby murder stick. It was like some crazy neck down massive case, and he had a break on his, and he was always like, he's like, all right, if you miss or something, I'm gonna do a follow-up shot. And I'm like, I got no earplugs right next to his rifle, and I'm like, I can't miss. My ears. Yeah, anyway, I haven't been nice to my ears, but that's not the reason. It's just because I'm old. Do you hear the kids had the little ringtone things on their phone that like only young people could hear? That's so clever. Oh, that's so clever. I don't think my friends and I would have been clever enough to come up with something like that. But to literally use old people's old bodies against them to communicate amongst yourselves without them knowing is wonderful. I don't know, there's something just incredible about that. But yeah, Class D amplifiers nowadays would be able to, even those high frequency, only the young people can hear it sound, they would be able to amplify even that stuff. So that wasn't the case. You go back a couple decades, when they first introduced Class D, it was subwoofer only. And the only reason for that was just, subwoofer is under 200 hertz, so all you need is a carrier that's like 10 kilohertz or so and you're fine. So, Okay, other rundown topic stuff that I want to mention. For the homework problem 1, a lot of students, I think I've clarified it a little bit, but a lot of students with the first homework problem, which is calculating with a Class D amplifier, how much does a carrier create an issue for distorting the output in a Class D amplifier. That output circuit, you're just going to treat it just like it's a circuit from EE210. So you have a carrier frequency and magnitude, you have a signal frequency and magnitude. Both of them are just going to be a phasor. It's just going to be a voltage, amplitude, at a frequency. So you're going to analyze that output filter, which is like an inductor and a capacitor and then an output resistive load. You're going to analyze, it just basically becomes a frequency dependent voltage divider, and you're just going to analyze it like you would in 210. So it's not a you don't need to overcomplicate it. It's just two circuit problems where as the frequency changes, the impedance of the capacitor and the inductor changes. And then the best technique, so just to warn people, the technique for, the way I teach this class is when we go over buck and boost converters, I say you are going to design these the same way you would if you were working for a company and they said design a buck or boost converter for this circuit. And that is to say, you will identify the operating parameters of the buck or boost converter you choose to buy, and you will design around it. So based on the switching frequency of the converter, based on your requirements for average current, based on the limits of the inductor that you want to use, you are going to identify reasonable parameters. You're going to solve for inductor and capacitor values. The nice thing is it's basically cookbook approach. So it's a cookbook approach to doing this. It's a step-by-step process you can follow to choose your capacitor and inductor sizes to meet certain desired parameters for a buck or boost converter. And the cookbook is posted online. So the cookbook is the sort of design guide by Texas Instruments, I believe. It's posted there. You don't have to overcomplicate it. Now, there are classes you'll take in this program that go a little more into the theoretical nature of these converters. So if you want to analyze a switching converter, it is actually a giant pain in the butt because you have to deal with every mode of operation of that MOSFET. So you have to deal with, okay, what is this circuit doing when the MOSFET's on and off? And also, in that little nanosecond of time when the MOSFET is turning on or turning off, you have to analyze the behavior of the circuit. And that's really the critical part because that nanosecond of turn on and turn off for the MOSFET is when you get most of your losses. It's also where you get what's called shoot through sometimes, which is there can be moments in time when your MOSFET is basically a short circuit between power and ground. So you get all sorts of weird harmonics that can happen as well. These regulators, when you're designing them in practice on a PCB, your considerations are much more stringent than the stuff you did for your project. So your project was all really no frequency dependence for these switching regulators, especially when you have like a feedback like this. It's very common with buck and boost and linear regulators to have this feature where you get to program the output voltage by choosing the resistor divider that feeds back. But a challenge is with buck and boost converters, if this thing is switching like possibly amps of current at a frequency of close to a megahertz, it is generating an enormous amount of noise. And so if that noise interferes with this, it can create instabilities in the feedback path. We've done projects in the past where that shows up. And normally the good thing is the instability is just a higher frequency than what we're designing with. But so your issues become much more critical for like board design and layout and breadboarding with these high frequency switching devices. And I always like to tell students just think about it as loops of current, right? This is a loop of current. If you have some wire outside the board here, and that wire is switching at 1 megahertz, 1 amp of current, at 1 megahertz, this is generating a huge amount of magnetic flux. And that magnetic flux will be, flux going in and out of this loop here. So it will be generating current, it will be producing a voltage noise on that. The best way to avoid noise in these circuits is to keep everything tight. So you want to physically keep on, if you're doing a PCB layout with one of these regulators, you want to physically keep these capacitors and resistors close to the chip. Because the further from the chip away they are, the bigger a loop they make. So if you go back to your physics class, the bigger the cross-sectional area, the bigger the flux, the bigger the induced current. So keeping things, and one really nice thing is nowadays, if you look at a data sheet for one of these switching regulators, they will have a suggested layout. So that suggested layout will show you at least an example of, here's one way you can wire this thing up to make everything as tight as possible. So, but it also means, unfortunately, to do labs with modern regulators, we really can't, we can't use modern chips to do labs and breadboard it, because if you do a breadboard wire, it's just game over. There's no way you're gonna get feedback noise. It's gonna cause a problem. But we will do a switching regulator lab. It's just not gonna be quite as exciting as you might think. Or it's not gonna be using practical chips. Maybe you have questions about this? Yeah.
So that kind of goes into the, at least on our PCB, the idea that based off our trace, that could create back EMF to what our circuit is, or what we want our like circuit output to be, just based off of the trace sizes and or how we create the circuit.
Yeah. So back EMF usually is a term that only refers to like
Transformer.
transformers or motors and things. Yeah, but you get EMF, right? I mean,
Yeah.
so you get all these loops produced, and the ground plane. When I in one of the videos when I talk about the ground plane, the real benefit of a ground plane is almost every signal ultimately is tied to ground, and so if you have a ground plane, the loops in your circuit, rather than the loops being on the surface. Oh, come on now. All right, watch your head. We're gonna go for it. Little circle, big circle, right? Oh. That almost hit your head. I'm sorry. That was more of a line drive than I thought. It did hit the can, but it was nowhere near going in the top. It just kind of arched to
Come over forward.
make it. So, oh, that's a good one.
Ooh, that's nice.
Right. So, if your ground is like, say you got a connector here, and your ground is like some wire that's going to your chips or whatever, and then you have another power thing. That powers another chip over here. When this is the case, your power to ground loop is this whole thing through here. When the ground is a plane on the bottom of your board, then in that case, you're going to ground here, and in this case, the loop that's produced is really a vertical loop that's sort of overlapping here, right? So you basically have your loop is in the cross section of the PCB rather than on the surface of the PCB. And the PCBs that we're using are only 1.6 millimeters thick. So even for a long trace, it's a very small cross-sectional area. And that's one of the big reasons why we like to use ground planes. But I mean, imagine when we talk about ground loop noise even, imagine something like this. If you have ground loop noise here that's at like 1 megahertz or something like that, even if it's very small, this comparison is going to be it's going to go for a ride, right? It's going to, when it's operating close to the proper output voltage, which it almost always is, it's going to be like any noise produced here is going to show up here, which is then going to show up here, and so it's really easy to produce this sort of disastrous feedback, instability. So, yeah.
How expensive are ground planes generally?
I mean, for you, they're free.
Yeah.
So the boards that we use are 1 ounce copper. That means it's 1 ounce of copper per square foot of PCB. So I mean, an ounce of copper is maybe, for the copper they use in circuit boards, an ounce of copper is maybe like $2 or so. So you're talking $2 per square foot is the ground plane. Another thing to note though is like the circuit boards that we use, if we want to do a ground plane, we have to use like the bottom layer, and we also probably have to use the bottom layer for traces. In a more advanced circuit board, where you'd have more than 2 layers, a more advanced circuit board, you'd have, the iPhone I think is 12 or 14 layer PCBs, and when you're doing that, it's very easy. You'll almost always have 1 layer that's dedicated to ground, maybe multiple layers. The other thing is, if you work for like an aerospace company, they'll often have metal layers in the PCB that are meant to shield from like radiation. And so now you're using them as a ground plane, and also they're like made out of some exotic metal that will absorb, you know, gamma radiation or something like that. So, so circuit boards do a lot of crazy stuff. That's you know, and if you ever go into advanced circuit board stuff, there's a lot of companies actually around this area that do this crazy stuff. Like they'll put, you know, it's not lead, but it's exotic metal, yttrium or something, in a plane on a circuit board, because that circuit board's going, you know, commercial aircraft count as being in space in terms of radiation, right? Because you're not, I mean, you're really getting bombarded when you're flying. Like you're getting hit. You're up 5 miles or so, right? You're getting quite a bit of radiation there, but more importantly, the circuit boards are, and so you don't want them to have an issue. Satellites are even worse, of course. Defense systems, gosh, right? They're terrible because they're not just solar flares. They're like enemy, you know, EMPs, right? Because you know, war breaks out between two countries that know what they're doing. It's EMPs, right? Everything's gone. All the satellites are gone, right? So we try to help them survive, but we're satellites and anything on the ocean, on the surface of the ocean, is gone in seconds, right? So, but designing for that sort of stuff is usually, there's other reasons why you want to have ground planes. Also, they're often used for thermal dissipation. If you get like an iPhone, one big concern with an iPhone is you have this circuit board that potentially, when you're using it a lot, this thing is dissipating several watts of heat. And you have a very small circuit board, an increasingly tiny circuit board. So, you know, the challenge of dealing with heat, which is not something we do in this class, becomes almost as big as the challenge of dealing with ground loop noise and things like that. So, and that's another area though where a ground plane is nice because it's kind of like a big giant heat sink. It's not as great when it's inside, when it's in a middle layer. It's better if it's on an external layer, but it has that purpose as well. So, okay, other questions? I just kind of wanted to set the table for the next homework and the videos. So we'll have a little more time on the homework, and I do want to answer questions, especially I want to do buck and boost regulator questions on Monday, so I'll probably at least start the process of those. But for those who haven't done it yet, it is a cookbook process. So it is identify the stuff you need to know, identify the critical issues, make reasonable assumptions, which is the toughest part, where do you assume 30% or 40%, stuff like that, and then build your design around that. And again, for batch 3, if you submit your board late, if you submit a board, anything, again, it could be business cards or whatever else. If you submit something late, just send it to me. So email it to me. If it's after tonight, just email it directly to me on Saturday, and we should be able to get it with batch 3. Also, I'm sure some of you will have boards that come back screwed up. Sometimes, like, something happens and like a whole layer is like messed up. We don't know why, but the good thing is we'll have enough time this year that if we need to, we can probably, if you get a board back and you realize quickly something messed up, we might have time to reorder it before. So there might be another order going out later. So anybody who's got personal projects or want to do something nifty or want to make some light stuff up or something like that, feel free to keep working on that over the weekend while you're celebrating, you know, Britney Spears' freedom. And it's still, all the whole lecture, the laptop is still bricked. This is not a good sign, right? Look at this. I even restarted it when I wasn't supposed to. Yeah, that's what I did. Okay. I guess I'll just post this.